It's
Yeah.
much
Okay. So I think we may start now, and let me say a few words. So good morning or good evening, everybody. And I'm Zhouping Xin from the Chinese University of Hong Kong. It's really my honor to chair today's speaker, Professor Yanyan Li from Rutgers University. And Yanyan is, I know Yanyan, well, real young kids from China. And so Yanyan was always a star, even when he was a student in China or in Current. He was a star student in Current. So one of my job when I was in Current, the director was David McLaughlin at that time. He said, "Oh, Zhouping, you have to find a good student from China as good as Yanyan." But that was very hard to find one. And Yanyan graduated from Current in 1988, and then he went to Princeton as an instructor. And after 2 years, right, he moved to Rutgers, and then he became a professor, full professor, now the distinguished professor at Rutgers University. And Yanyan is always a leader in analysis and in PDE, has done many very interesting and important work. And he got many honors, including SM speaker. And he's a distinguished professor at Rutgers University. He's also he's leading the Center of Nonlinear Analysis at Rutgers University. So today is great for us to have him to give us a seminar. Yanyan is always a wonderful speaker, so we expect more. Without further delay, let me ask Yanyan to do his seminar. Yanyan.
Oh, thank you. Thank you very much, Zhouping, and for the very kind invitation and also very kind introduction. So it's a great pleasure to be here and very good to see Zhouping online. So it's better to see face to face, but this is also good. So so I will. So it's 45 minutes, right? Yeah.
Yeah, 45 minutes. Yeah. Then we have about 10 to 15 minutes questions. Okay. Yeah.
Okay. Thanks, Zhouping. So today I want to describe some recent work with a student of mine, and so so we are yeah. So this is about. So I will start from describing a little bit previous things in this area. So the title is gradient estimates for the insulated conductivity problem. So this is what our new work is about. And so if we taking Rn, so we taking Rn and we take an omega open set and we take omega prime, its closure is in it. So then if this is harmonic, if we control H1 norm, for example, and you will have gradient norm in here. So of course, you will control all derivatives inside. So I will only talk about gradient in this. So okay. So is it okay if I do this?
Yeah, it looks better in this way. Yeah.
Okay. So I can have one page this way. Yeah.
Okay. Yeah.
Okay. I can make it slightly bigger. Okay. So
yeah,
now if I still look at this, if I look at the coefficients, so I look at equation like this, and the coefficients is elliptic, and if we assume H1 is less or equal than 1, and but you assume your coefficients is somewhat smooth. Yeah. So then, like Schauder theory will give you derivative under control. So if you don't assume that Aij is so regular, so you only assume ellipticity and divergence form, and you give control of H1, so de Giorgi theory will, de Nash will tell you that de Nash. So will tell us that U Holder norm is bounded by a constant for some alpha. So the alpha, depending on this ellipticity lambda lambda, this omega prime. Yeah. So this is de theory, de Nash theory. So if you look at a situation that the so if now let's say you have a one ball like this, one unit size ball, like a unit ball, just a unit ball, or very smooth domain. So let's take another ball, unit size. Let's take 2 unit ball, and these are unit size away. This is unit size away, and omega, yeah. And the only thing is the small. This is small. The distance between these 2 balls are very, very tiny. So epsilon is very, very small. So in that case, if you look at your coefficient AK, so you define your K, your AK to be constant K inside here, a constant K inside here, and you take 1 outside. So your coefficients, you have ellipticity, and K is belong here. So you have ellipticity, and coefficients is not continuous. So not continuous. You have a jump. So in this case, so the question some time ago was whether or not the gradient is bounded. So that's a question. This does not follow from de Nash, because this is not de Nash only give you holder. It doesn't, in general, doesn't give you. So, but of course, if we just look at qualitative behavior, so this is called transmission problem. So now you have a jump discontinuity, and your coefficients on both sides are very nice up to the boundary. And then solutions will be smooth in each subdomain. Will be smooth. So for example, smooth here up to the boundary, smooth here up to the boundary, and smooth here up to the boundary. Okay. So, but they form an angle. Their first derivative will be discontinuous. So, but what is not known, what was not known before is this gradient may blow up when epsilon go to 0. So that was not covered by earlier theory for transmission problem. If we just look at the qualitative properties, I mean epsilon dependent norm control, it should be known like 60s, 1960s, it was known at that time. So Ivo Babushka and collaborators in 1999, they look at fiber reinforced materials. I think they have 2 papers around the time. They observed numerically for certain linear system of elasticity. They use the so-called Lemay system. It's I will describe before later. Yeah, it's a homogeneous isotropic material. So you end up with Lemay system. So in that case, they observe that this L infinity norm actually is independent of epsilon. And my colleague, Michael Vorgelius and Bonnetier, they were actually both former students of Babushka. So they proved in 2 dimension, that if you take 2 balls and then they proved that if these two balls are touching like this, so you have K inside as coefficient 1 here, then they proved that actually gradient U is in L infinity. Yeah. So of course, if you proved this is epsilon independent, then by taking limit, you will know that you will have this. Yeah, you will have this. So the method here is to use complex variable method because this is two-dimensional case. So then, so my colleague told me about it. So then, and we extended this result, and so we proved that quite a number of months later. So it's like 8 months later. We started 8 months later after their work, even though the year is the same, but we are later. So we proved the following situation. So if instead of piecewise like Laplacian, right, cross, yeah. So we can extend it as a second order divergence form elliptic equations in all dimensions with piecewise smooth coefficients, and having this, the jump is only cross smooth surfaces. So we proved that actually all these gradient U norm are epsilon independent. So later with Nuremberg, we look at the elliptic systems, including linear system of elasticity, and we extended the result to systems. So it also works for second order divergence elliptic systems with piecewise smooth coefficients. So gradient U will be bounded, independent of epsilon. So what is linear system of elasticity? Linear system of elasticity is like this. So the number of equations here, U1, U2, Un, and the number of variables, x1, x2, xn, are the same. So, and these are the coefficients. So it has symmetry. So when you switch ij and alpha beta, so like this, so they are the same. And you can also switch I alpha, and they are the same. So it corresponds to when you set up the equations, you have all this translation and rotation invariance. So you end up with this symmetry. So, and the ellipticity is like this. So you look at Aij alpha beta, this cos I alpha is n by n matrix. This is n by n matrix. And you have this positivity. So you test it on symmetric matrices. So this is linear system of elasticity. The simplest one, so this is the homogeneous isotropic. So it is like this. Mu is a positive constant, and the dimension lambda plus 2 mu is positive. So this is the system. So if one wants to extend the results, we usually first work with equations like such equations, and then to extend to system, we would first try this. Yeah. So here is the we record the setup now. So take a omega in Rn, and take two domain D1, and D2. These D1, D2 are unit size, so they are smooth. Let's say they are smooth, unit size. Yeah. And there's an epsilon here. which is small distance between them. All these other distance are unit size away. And phi is a smooth data. So then look at the equation. So we have maximum principle. So maximum principle tells you L infinity is under control. So our AK is K inside, K here, and 1. So the work I mentioned with Vargalius says the L infinity norm of the gradient is bounded. So it's bounded by a constant dependent on K, but independent of epsilon. So it depends on this K. So now the question is, what happens if K goes to infinity? So what happens, for instance, what happens to this gradient bound? And or K equal to infinity, or K equal to 0, this is insulated conductivity case. So we have some new result recently and for this case. So how about for K equal to 0, goes to 0? So for K equal to infinity, so, well, this should have a meaning, because when we just put coefficients like infinity in here, infinity in here, and 1 in here, so there is some meaning. One needs to make sense of it. We can, if we put a boundary data phi, we can look at a K here. Instead of A infinity, we look at AK, and you have UK, as we defined before. Then this UK will go to U infinity, will goes to U. This U, in a property sense, uniquely. So one can prove that. So this U is the solution to this problem. So these are some kind of like engineering. One is a book, one is a paper. So what they are interested in that. So they actually showed some solutions, special solution. So some special solution in it, and they show that the behavior is in n equal to 2 is this behavior. So they showed by examples. And then Amari, Kang, and Lim, this is the first work for K equal to infinity. And then there are work by Amari, Kang, Li, and Lim, and Yun, 2007 and 2009. And there's Alan Bao and Biao Yin, and myself in 2009. And so, and then the result is when n equal to 2, one can prove in this local situation, it is always less or equal than this. And in 3 dimensions, it's epsilon log epsilon. And for n greater than 4, it is epsilon minus 1. So that's the rate. So namely, you always have bounded from above by this rate. And there are also examples, phi, when you give a probability phi, and the rate will be exactly that. So those are optimal rates. And for linear system of elasticity, like the Lemay system, so then, so when we make so in that case, instead of we have ellipticity constant k1 and infinity 1, so one can say, if we look at 3 sets of mu, okay, mu1 lambda 1 here, mu1 mu2 lambda 2 here, mu3 lambda 3 here, they are all elliptic. So this is the ellipticity somehow. Yeah, keep it in the right range. So in that case, so the L infinity dome is under control. It depends on this mu I and lambda I. So that's the earlier work mentioned with Nuremberg. And so now question is what happens when this ellipticity degenerate? So when they degenerate to infinity, these were studied by Ji Guangbao, Haigang Li, and myself a few years ago. So we look at partially infinite coefficients. In some sense, it's like mu equal to infinity and this is equal to infinity. Or you take this two parameter goes to infinity, you look at a sequence of solutions, they will have limit, and you call that limit the solution. So in that case, so we proved these bounds. We have these bounds. So these are like in the equation case bound, upper bound. And we also mentioned that when this k goes to ellipticity goes to infinity, what should happen? So for n equal to 2, as k goes to infinity, this ak is still like a k and 1, look like this situation. So in this work, so they showed that actually the rate should be constant over 1 over k plus epsilon. So so if we look at the case like my drawing work with Vogelis, that's k equal to a constant. So then you see if it's a constant, this epsilon will not play a role, gradient u will be bounded. And if k is infinity, I wrote this rate wrong. Okay, so I should have, I think it should be square root. I may have, I have to check, so I have to match that, yeah. Okay. I think it should be less than c over square root. So, well, there could be some number, maybe a square or square root, yeah. Anyway, so it's a more satisfactory estimates in a way that not only giving infinity, it gives you the rate as k goes to infinity. So this was first done in this paper, in these two paper. In these two paper is in they look at the case like two boards, two unit boards, and they can allow more general situation like different radius boards, and in R2, and they are harmonic somehow, satisfy that equation, and at infinity they prescribe they have a rate with a harmonic function, something like that, like this setup. So H is harmonic. So in that case, they identified these rates. So these rates. So then proof was given by Hongjie Dong and Haigang Li. Haigang Li, yeah. And they proved more results. They proved more results, yeah. So I am just staying with L infinity. So this is two-dimensional case. So for k equal to 0, insulated case for n equal to 2 again. Well, this case is kind of dual dual problem if you set it up in R2 at least. So it's a dual problem to the k equal to infinity case. So actually the right rate should be 1 over c over root epsilon. So by work of Amari Kang Lim and Amari Kang Li Li and Lim, 2007. So this is the case. So you are given a harmonic function in R2, and you look at U is outside the balls, outside these two balls, and you give normal, zero Neumann condition, Then the epsilon is here, the distance is small. Then the rate is c over root epsilon. So the insulated case then for higher dimensions, insulated case. So you put k equal to 0 here, and 1. So actually what you do is you put the Neumann condition here. And say Laplacian U in this region. And with Allen, Bao, and Biao-Yin, we proved that the rate is this rate in all dimensions. So this is for all dimensions. So we know that this is sharp. This is sharp. It was already proved, the sharpness in this work. This is sharp. Yeah. And it is also dual to the infinity case. So it's sharp, it's known. So it has been open for a while whether or not for n greater or equal than 3 is sharp. So namely, is it possible to actually improve this rate? So, and for n equal to 2, again, it is desirable to know these estimates, how this estimate depending on k and epsilon. So therefore, the k equal to infinity case estimate will follow by simply sending k to 0, k equal to 0 case will be, yeah. So, and in n equal to 2, this was done in the same paper mentioned, Hong Jie-Dong and Haigang Li. And in the case of a global case in R2, take away 2 balls, and with epsilon distance here, Neumann condition, prescribed a behavior at infinity like a harmonic function. And that was done earlier by Amari Kang, Lim, and their paper. So this is so here they localized it, and also they extended it for 2 strictly convex domains, not only balls. So they have this rate. They have this rate. So again, for k equal to 0, even for k equal to 0, for n greater or equal to 3, this has been not known whether or not it's sharp. So as mentioned earlier, it was proved with Bao and Yin. We have this rate. Well, Yun in 2016, this year was wrong. So apparently, maybe 2009 or 11. That's our second paper. So okay, this year was wrong. This is probably 2009 or 2010, something like that, around that. I don't remember. So this is more recent. So Yun. So he looked at as n equal to 3 case, wants to answer this question: is it really sharp? So he looked at this n equal to 3 case and look at in R3. So put a unit ball here. This is a unit ball, and B2 is also a unit ball. So this is a unit ball, And this is a unit ball with epsilon distance. Okay, this is epsilon distance. And we take a harmonic function outside. At infinity, we take prescribed to be y. Y is harmonic function. Laplacian y is 0. You take a harmonic function y, okay, and you at infinity you assume this. You look at that, and then Yun focused on this line. Okay, so he showed that on this line, the gradient size, this is x0 there on this line. So it's exactly this rate. So it's this rate. So it's less or equal than this rate and greater or equal than this rate. So that's the rate on this line. So this line, you see, this number is less than 1/2. So this is 1/2. So in principle, it gives you a possibility of showing for this one, you know, at least on the line, is better than this rate. This is what it says. So at least on this line, there's a room, okay? So here, I will describe a recent work with Zhouping Xin. So he's a student, current student of mine. And so we look at this situation in R3 and trying to understand whether or not the rate is sharp. Yeah. So it turns out that we prove that it's not sharp. One can actually improve it. So we take any two smooth, strictly convex domain, this D1, D2, D1, D2 should be smooth, unit size, strictly convex. Unit size. So it's not related to epsilon. Yeah. So this is also unit size. So yeah. So there's epsilon here. This is epsilon. So Laplacian U equal to 0, Neumann equal to 0, Neumann equal to 0, and outside you give a nice data. So one can show that the gradient norm is actually less than C over root epsilon, but there's a beta here. So you can gain a beta. This beta is what you get. Beta is positive depending only on n, d1, d2, and omega. So you can improve the earlier result. So I will describe the proof. And of course there are many open problems here still. For example, like can one actually so you see in this example, you know, nice example, you actually pin down this rate, right? Yeah. Is it possible, like whenever you have a domain, you have two unit ball like this, you can actually pin down the optimal rate, namely a better one would be actually pin down the gradient profile, okay, the dominating profile, if one can identify that. And in general, if it's not a ball, so how it's related to the curvature at this point, perhaps something like that. Yeah. So how does it depend on this domain, for example? Yeah. So this rate. So these are need to be studied further. So we are just having a preliminary step, just saying that the rate known before is not sharp. One can actually improve it. So let's take a simpler case. So let's say, let's just take a simpler case. We just take this two dividing surfaces is this. Let's take R3. So just a parabola up, parabola down. One is positive, one is negative, and this distance is epsilon. And we take a point. We try to estimate the gradient there. So we take an arbitrary point x0. We show that here we gain a beta. Actually we gain a little bit more than that. It's actually it's c epsilon plus x0 prime square and raised to this power. So when x0 is further out, so it's smaller. So for simplicity, we will just take a point. Let's say we take the point. Okay, right now we take a point. So this is just redraw it. We still take this point. What do? We take this point. We take this point. We take this point. We call this height is delta, more or less. You know, we give a number. Yeah, this is the scale. This is the right scale. So more or less like twice this height or one. Yeah. So this is the height. That's the right scale to work with. So we are going to identify a positive number gamma. So this will be a small number independent of epsilon. It's like a number which only depends on the shape of this dividing surface. Okay. So our notation is omega x0 r is a cylinder around this x0. So it looks like this. So we are going to look at the some like this. So we work with this cylinder. Okay. So we focus on that and work with R. So we work with the R in this scale. We want to work with this in this scale. Yeah. We first look at that in that scale with that R. So this delta is here. So gamma is a universal positive number. So we work at that. And then then we prove that without loss of generality, we can say U is bigger than 0, less than 1. So then we only use the information that is in the like an annulus shape, right? It's a 2R minus 4 over R. Okay, and on the top, that refers to this cylinder. So one cylinder and another cylinder inside. Another cylinder is somehow inside. One cylinder outside and another cylinder inside. So it's like a shell, but with this funny shape. Yeah. We work there. So in there and on top, meaning when they intersect here, you do Neumann. You do Neumann. When here you have Neumann. So and you have a shell region, and with R, any R in this range. So R is allowed to vary from there. So then we prove a Harnack. We prove the sup and less than the inf. Okay. So this constant C is independent of R, independent of epsilon, and independent of U. So as long as your R is kept in this range, so you have a uniform C. So for simplicity, let's say if you take x0 is just the origin, so then we are taking a cylinder like this. Not the shape is not too much twisted. So it's easier to visualize, right? Yeah. So so now we work with R, then which means we work with R like this. It should be a gamma over 2, but we don't care. So we just say we work with root epsilon, but minus a little bit. It's bigger than root epsilon. So you want to go out a little bit. Yeah. So we are able to go out a little bit. So going out a little bit is directly connected to the improvement of this beta. So we are able to go out a little bit to still have a Harnack. We are able to do that. So this Harnack this Harnack plus some maximum principle will tell you this one you will know that in the root epsilon one, you are going to gain. Not only is bounded by C, you are going to gain epsilon to some power. So this HANA will tell you that if you take this cylinder like root epsilon size, so your U has oscillation in there like epsilon power. So this power, because of this power, we are able to gain earlier estimate by beta power. So now we are in this situation in a way, okay? So if we want to control this at the center gradient U, if you want to control gradient U at the center, you want to control this. So you want to control that better than 1 over root epsilon, better in the quantity epsilon to some beta power. So we first say that when we go to horizontally, we go root epsilon. So the height, vertical height is epsilon. We go horizontal size is root epsilon. We take this cylinder, we prove that the oscillation of U there is like epsilon power. Once we have this, we are able to reduce it to the following situation. So we are going to somehow, we take out this cylinder type, but with varied with this shape, we are able to prove we are going to make a transformation to a shell like that. So x prime is like 1, and the height is some delta height. Delta height. I think for this case, delta will be a root epsilon height. So we are going to have a flat shell. We have a flat shell. And the equation, then when we make transformation here, so from this shape to this shell, the transformation is not singular because it's in the gradient epsilon. If you take larger gradient epsilon, more larger, the transformation to flat will produce singular transformation. So this is not singular. So now we are going to be in this situation, and we know the coefficient, the equation will be like this. I think the right-hand side can still be 0 in this case. Yeah. It's 0, yeah. And maybe, okay, yeah, it should be still 0. So the coefficient C alpha is under control. So in here, it's like a unit size and height is root epsilon. So this is under control. So this has something to do with we are only taking out a root epsilon size, height epsilon, root epsilon. So that gives you a good coefficient. So then in here, so we know that then in here we have Neumann, kind of Neumann, but not Neumann, it's Neumann like this, okay? So it should be something like Nj dju, Anj dju equal to 0. So this is just the right boundary condition when you integrate by parts. So this is right boundary condition, elliptic equation inside, good coefficients, but the shape is not a regular shape. It's kind of flat like that. So you have estimates of UL infinity, gradient UL of infinity can be controlled by L2 norm, half 1 over root epsilon. Yeah, if you want, you can replace, you can also, if you like, you can replace this by UL infinity norm. Yeah. That's good enough for us. So you can get this estimate, okay? So such estimate were established in earlier joint work with Borgelius and Nuremberg in this case. So for such type of estimate. So now we can reduce to such estimates, and using this oscillation, and we are able to improve earlier insulated case estimate. Yeah. So I'll stop here.
Okay, thank you very much, Yanyan. And now we can open for the questions. Oh, I see a question. Oh, Yanyan, you see
Yeah.
there's a question answer section. There's a question from Daniel Spector.
Oh yeah.
Yeah.
Okay.
You answer that.
How do I work? How does it work?
Did you see the Q&A section?
Yes. Okay. Oh yeah, I see it. Oh,
Okay.
I'll read it. Okay, I got it. I should read it, right?
1 second, Yanyan. Actually, if Daniel Spector raised his hand, or I can give him permission to speak, he can speak up.
That's right. I think that's better. Maybe he just speak. Yeah. Yeah. We know each other. Yeah.
Hi.
Hi. Where are you now, in Taiwan?
No, I'm in Japan and Okinawa right now.
Okay. Yeah. Okay.
Thank you very much for your nice talk, Yanyan.
Oh, thank you.
I had a question about this. This is nice proof. Have you done the computation for the higher order contact?
Higher order contact. Yes, I think we know. I think we our way should so the method will perhaps give higher order contact. Yeah.
So that you can get something which is, with the higher order contact, you get better powers of epsilon, like not so negative.
Yes, so this method should give that. Yeah. So far, what we do not know how to handle is the system. Actually, the mainly we use the maximum principle.
Mm-hmm.
Yeah. So this method, so you see that this only enters in this with this transformation. So in which range? So for example, if it is quadratic, then the root of the height is the right right size. So the root. So if you have another power, so that will, if you just make the transformation, you know what is the right rate, right size. Yeah. So they all connect together. For example, our earlier work, when getting this 1 over root epsilon, we only need to cut out, if you are quadratic, you just cut out, basically you just cut out root epsilon. So then we don't use information outside. So just this part, then the transformation will automatically, the method will lead you to the result.
Mm-hmm.
So,
and maybe you don't have a proof in the system case, but do you have a feeling that it's the same in that way?
We have been working, we haven't got it yet. Yeah, for the system, if you do root epsilon, it's the same. If you are willing to give something like measure in terms of L infinity. For example, for system, so our earlier work already gives something like this. The gradient U will be controlled by C over root epsilon. It's the same proof, and L infinity. So this is okay. So but you'd like to control it by L2. We don't quite we don't quite see it. Yeah. So L infinity, then there's no difference our earlier proof to reach here. So but if you put L infinity for system, improve this, we don't see. So that's we don't see. So the new step, somehow we use even allowing L infinity here, we still don't see.
Thank you.
Okay, so any other question or comments? So yeah, I have one question. That so the first question is, do you have an estimate on the beta, the last result?
That's the thing. We don't. We would like to have. Yeah. That beta is because of this Harnack part.
Yeah.
The Harnack. So we don't have a good beta.
I see.
Yeah. No, we don't.
Uh,
So we only know there's one beta, so we don't have a good beta.
Another question is, so in your these descriptions, so that this A cat X is piecewise constant. So if this guy is variables, for example, in the region in the ball, somewhere this guy is variable and degenerate, be 0 and some point is not, then do you expect a similar result?
So if A of X, so go back here.
Go back, yeah.
So if it's so if let's take AK, just take this, right? Yeah.
That's right, yeah.
So if this AK is a function, smooth function somehow,
Yeah.
if there's a lower bound,
Yeah.
smooth, yeah, with normal control, for example, the gradient AK bounded thing, then it's okay. But if you take away that, so all our results, we do not cover that.
Because in for example, the Lamb system also appears in compressible Levi-Stokes equation, and in the vacuum case, if the some point touch vacuum, then actually the AKS goes to infinity. But it's not every point, maybe some point. And so in that case, so it's a you don't have upper lower bounds.
Yeah, that's very interesting. So maybe you can tell me some, yeah. So all our work have not been addressing that at all.
Okay, okay.
Yeah.
Okay. Okay, any other question? Okay, if not, let's, I think you can, you feel free to ask more questions in coffee hour, okay? So let's thank Yanyan for excellent talk. Thank you very much, Yanyan.
Thank you for the audience, for participants and for the patients.
We will see you in the coffee hour. Coffee hour, okay?
Coffee hour. How does that work though?
I think Daniel sent you already another message about how to go to the coffee hour.
Okay.
Yes. So you received an email with another link to a Zoom meeting, and with a password. You just have to press this link and enter the password, and then we see each other with your favorite drink in the coffee break. And everybody, every attendee received as well such an email, and you're warmly welcome to join the coffee break, please.
Thank you. Great. I will join.
Okay.
I will close the meeting then. Yeah.
Yeah.
Okay. Good. Yeah.
Okay.
So that's today, and so we see you in the coffee hour. Okay. Thank you very much.
Yeah.
See you then.
Thanks for the participants.